As you can see in this slide, two Europe's leading blast furnaces plant, left and right, as you can see, did the opposite thing with the nut coke. One increased the nut coke size, the other decreased it, and both claim success. How is that possible? So, as you can see, the left side company increased their nut coke screen size from 30 to 35 mm. Why? To get more nut coke available. They raised their rate from 35 up to 50 to 60 kg per ton of hot metal. Now the result, they reduce total fuel consumption because the extra nut coke near the wall improved gas efficiency. This was the logic. As for the right company, they did the opposite. They reduced the screen size from 30 to 25 mm. That actually lowered their nut coke rate about 40 kg per ton hot metal. But it increased the proportion of coarse coke. The result, better permeability in the furnace. So, which is right? The key takeaway is this: there is no single correct nut coke rate. Your strategy depends on your coke quality, especially the MICOM 10 and CSR values, and your furnace objective. If your coke is strong, you can push nut coke for fuel saving. If permeability is your problem, you might want less nut coke and more coarse coke. But watch out, if your coke strength is poor, high MICOM 10 above 5.8%, you will generate too many fines. That hurts permeability and makes small coke reach 2 year. So always align your screen size and nut coke rate with your coke quality. Now coming to the 8% threshold, that is maintaining permeability with the ferrous fines. So now let's talk about the ferrous fines. Those are small particles from the sinter screening and how grade, rubble or ore they behave. So they are the cheap, but they can kill your permeability if you are not careful. This slide shows a hard data driven rule from 10 years of operation at Chorus Red Car blast furnace. The key parameter here is the composite coke size after direct reduction, what we call the harmonic mean size or HMS. When that composite coke size is small, below 40 mm, your permeability is already poor, no matter how many fines you use. But when your coke is large, above 42 mm, you have a window to use fines safely. The critical number is 8%. 8%. So if the total of ferrous fines plus low grade ore exceed 8% of your burden, even with good coke, your permeability resistance coefficient start to climb. That means the furnace becomes harder to blow, you lose production and risk stave damage. So the rule is simple. If you want to use cheap fines, first make sure your coke is strong and your composite coke size is above 42 mm. Then keep the total fines plus low grade or below 8%. That is your safety margin. Now coming to the hearth protection mechanism or condition, we can say the coke HMS, as we have already discussed, this slide introduces one of the most powerful tools from the research, the composite coke size calculation. Why is it so useful? Because what you charge at the top is not what arrives at the hearth. Coke get consumed, especially the nut coke. The report proposes a formula called harmonic mean size HMS. It combines the size of your coarse coke and nut coke after accounting for direct reduction. And here is what the data shows. Look at the left graph. When the calculated HMS exceed 42 mm, your top gas utilization actually drops. That sounds bad. It means less efficient gas use. But look at the right graph. At the same HMS above 42 mm, your heat flux also drops. That is good. It protects your copper strip. So you have a trade-off. Below 42 mm, you get better gas utilization but higher heat flux, more wall stress. Above 42 mm, you protect the wall but lose a little efficiency. The experts at the chorus found that the sweet spot is around 42 mm. That is the compromise. The practical message: don't just measure coke size at the stockhouse. Calculate the HMS before direct reduction. It will tell you what is really happening in the lower part of the furnace. Now coming to our next important area. Now let's go to the laboratory. Thiessen ran a series of melting down tests that simulate the entire blast furnace journey. From 400 degrees centigrade up to melting, they tested three materials: sinter, pellet and lampor. The results are clear and sensational. First, reduction degree: how much oxygen is removed before melting. Sinter achieved 70%, pellets 63% and lump only 53%. So sinter is the most reactive. Second, the softening and melting range. This is critical for cohesive zone. A narrow range means a thin, stable cohesive zone. Sinter has a range of only 136 degrees centigrade. Pellet have a much wider range, 220 degrees centigrade. That means pellets soften over a long temperature interval, which can make the cohesive zone thick and unstable. Lampor is also poor with a range of 205 degrees centigrade. So what does this mean for you? If you want a stable, efficient blast furnace, especially when using low cost raw material, you want more sinter in your burden. Pellets and lumps ore can be used, but they will widen your cohesive zone and potentially cause gas distribution problem. The laboratory confirmed that many plant operators already suspect sinter is the backbone of consistent operation. So our final slide is about real-time control. How can you tell if your gas flow is healthy just by looking at temperature above the burden? The answer is central gas flow index. You have a probe with a 13 temperature sensor across the throat. Take the average temperature of three central sensor, divide that by average of all 13 sensor. That give you a quotient. Let's call it Q. So what German furnaces find? When Q is 3.0 or higher, furnace has a strong central gas flow, and a strong central gas flow correlate directly with better overall permeability. The furnace breathes easier when Q drop below 2.0. That means the center is cold, the gas is being pushed to the wall. That increases heat loss and risk damaging the strip. So here is the operational rule. Monitor this quotient every shift. If it falls consistently below 2.5, consider adjusting your charging pattern. Put more ore in the center or change your chute angle to restore central gas flow. And if you see very high central temperature with Q above 4, that might mean too much gas in center, which can reduce efficiency. The sweet spot is around Q is equal to 3. This is simple, powerful metric that any control room can implement today. No complex models, just thermocouple and a calculator.